Hello everyone, welcome to our TESOL Global YouTube channel. This is our FPGA video series where we will explain different aspects of FPGA. We will provide different examples and demonstrate some projects. In this video, we will start explaining basics of Verilog coding with some examples. This is the second part of Verilog basics. Verilog can be written as behavioral or structural description. Behavioral description is mainly used to describe the function of a design in algorithmic manner, which is similar to C language. Again, behavioral description can be written as continuous or procedural. In continuous, the data output assignments are continuous. As a result, any changes in input affect the output immediately. It is implemented using assign statements and the outputs are declared as where. In procedural, data assignments take place on specific events or clocks. It is implemented using always or initial blocks. Here output variables are defined as register. In contrast, structural functions are defined using basic components such as inverter, mask, and adder. Structural definition is like drawing a circuit in a board or paper where Verilog is being used to connect and arrange different parts of the circuit. Now we have example of full adder for both behavioral and structural description. In behavioral, after defining the input or output, the logic assignment is written with simple addition arithmetic operators, which you can see in this code. In contrast, the structural description is defined as full adder instantiation and the input or output are given in a certain positional manner. The connectivity of different signals in Verilog can be specified as positional association and explicit association. In positional association, the relative positions of different parameters are maintained or listed in the same order. In example below, the first and second parameters are general input, third is carry in, fourth is sum out, and fifth is carry out. So this structure will be maintained throughout the design. Now in explicit parameters, it can be listed in any order, but it requires to define which parameter will do what explicitly. Here you can see an example where in1, in2, carry in, sum, and carry out are defined in the parent module description, and A, B, C in, S, C are variables used in the present code inside full adder instantiation. Now in Verilog, there are two variable data types which are net and register. Net is used to interconnect two things. It is continuously driven, which means there is always a value, the net type output. Any changes in input affect immediately the output. Some common net data types are where or, where and, tri-state, supply 0 and supply 1. In contrast, register is used to store something. It commonly retains the last value assigned to it until next clock cycle. There are two register types which are register, REG, and integer. So reg requires to define the size. By default it is 1 bit, and in integer the default size is 32 bits and it doesn't need to define the size. So you can also have constant values in Verilog. A constant value can be specified in either the sized or unsized form. So the syntax for sized form is size, then the base and the number you want to define. So here we have some examples. The first one is 8-bit binary constant value. Second one is hexa number. Third one is signed integer. And the last two are logic 0 and logic 1 constant value. So next we will discuss parameters. So the parameter is mainly a constant with a name. It is not required to specify the size of the parameter. The size gets decided from the constant itself. So some examples are parameter h of I is equal to 20 or L of O is equal to 5, or parameter up is equal to binary 1 0 and down is equal to binary 1 1. So these two binaries are 2-bit binary numbers. Here HILO up and down are the name of the constant or are parameters. Now an example is provided to compile different things explained today. Similar to last times, we will first simulate it in Modelsim and then we will synthesize it in Quartus Prime and program MaxGen Development Kit. In this example, we'll blink a LED per half second using MaxGen Development Kit's 50 MHz oscillator. It uses clock divider technique to reduce the frequency of the LED toggle. This code uses both reg and integer variable data type. It also uses constant parameter. Furthermore, it is written in procedural behavioral description, wherein every positive clock edge, a counter is counting the value of the clock transition. When the counter value equals the division value, which is 25 mega, it represents half a second and causes the LED to toggle, otherwise the LED holds its last state. So before going ahead, we would like to ask you to subscribe the channel if you are benefited from our content. Also click the ring bell to get notification whenever our new video will be released. Stats show more than 50% of our viewers did not subscribe to our channel, so please subscribe and help us to grow our channel so that we can provide much more quality contents. Now we'll move to Modelsim simulation. Now you can see this Modelsim simulation window. Here we have already written the Verilog code for this example and also the test bench for this example. So here, as we said, we have the clock divider part, which is mainly this part. Here, whenever the counter value will be equal to our desired division value, the output will toggle. So here we can connect a LED at the output and we can see the LED is toggling in every half second. So we can change the time. So here we can change it to 1 second by declaring the div value as 50 mega. So now if we look at the test bench, in the test bench we are defining the time scale as 1 nanosecond, and in every 10 nanosecond the clock signal will toggle, and when it will reach to half a second, then it will cause this divided clock signal to toggle. So now if we see at the simulation window, you can see here, if I zoom it, so here is the zoomed view of the signal. So you can see the clock signal is toggling in every 10,000 picosecond, which is 10 nanosecond. And if we zoom it out, then you can see here when the time reaches half a second, then the divided signal or divided clock signal is toggling. So before it was 0, now it is toggled to 1. So this will be our output. So it reduces the speed of the clock by using the clock divider technique so that we can see the LEDs toggling at the output. So now we'll move to Quartus Prime. You can find the link of the video how to configure and simulate in Modelsim in the top of this video. It also have the description how to configure Quartus Prime to upload the code in MaxGen Development Kit. Now to start with the Quartus Prime, so we already have uploaded the code here. So now if we compile it, as we discussed before, it takes a bit to compile and synthesize. So now it is synthesizing. So if you go to the pin planner, you can see here we have selected the T20 as output pin, which will mainly connected in a LED in the MaxGen Development Kit board, which is this one. And we also connected the clock with the M9 pins. So this is dedicatedly connected with the 50 megahertz oscillator present in MaxGen Development Kit. So now if we run the programmer, here as well we already selected the FPGA chip for MaxGen Development Kit here. So you can either select it when you are configuring this program, or you can also do auto detect from here. It will automatically select your FPGA chip present in the MaxGen Development Kit. So now if you click the program and configure button and also select the compiled code, and if you click the start, then it will upload the code in the MaxGen Development Kit. And you can also see the LED is now toggling. So this is the LED which is toggling in every half second, and this is mainly toggling with the frequency of the MaxGen Development Kit internal oscillator, which is 50 megahertz we are using, and we are dividing the clock in a way so that the LED will blink or toggle in every half second. So now if we come back to the code, and if you want to blink it for 1 second, then we'll just comment the 25 megahertz and uncomment 50 megahertz. Then again we have to compile it and synthesize it. So it is now compiling and synthesizing. Here we are not changing any pin. We'll use the same pins. If you want to reduce the speed or change the oscillator, you can also change the oscillator. So you can see from the Maxten Development Kit user guide which oscillator pins are connected in which pin of the Maxten FPGA board. So here you can see the 25 megahertz is connected in M8 pin and 50 megahertz is connected in M9 pin. So it has four uh, configurable and dedicated oscillators. So now if we go again to the Quartus Prime, and if you go to the programmer, then just re-upload the code. Now click the configure, and if we click start, then the code is now uploaded in Maxten Development Kit, and you can see the LED is now toggling slower, or it's toggling in 1 second time. So in this way you can change the time for LED toggling. So this is the end of the demonstration. So this is the end of this video. You can download this Verilog course from our TESOL Global website. The link is given in the description. In our next video, we will continue looking at the basics of the Verilog coding with some example codes. Please subscribe to our channel for more videos like this. We'd like to thank those who already subscribed and helping us to grow our channel. Add likes and comments and give us suggestion of what kind of video you want us to make. Follow us on LinkedIn, Twitter, or X, and in Facebook. Thank you for watching. See you next time.